Okay, so we've got two definitions of acids then. The Arrhenius theory saying that an acid is composed of hydrogen, added to a group, dissociates in water to form a hydrogen ion. The acidic properties of the solution are due to the hydrogen ion. A base is a compound which dissociates in water to form hydroxide ion and a cation. Okay, so here we have the hydroxide ion over here and tagged on, bonded to our other group. Okay, now there's another definition then, which is the Bronsted-Lowry theory, which differs just slightly to this. But here's a key thing before that, and I can't say this enough, okay? Let's just start off with this. In the solution, strong acids dissociate fully, i.e. a 1 molar strong acid will produce 1 molar hydrogen ion. In a strong base, it dissociates fully as well, which means a 1 molar strong base will produce 1 molar of hydroxide ions, and that's the point about that. Okay, then the Bronsted-Lowry theory says that an acid is a proton donor, and quite simply then says a base is a proton acceptor. And this is a good basis to work on then from this. So for example, we've got water and HCl, which is an acid, forming hydronium ion, plus we have our Cl minus ion. And then we're looking at conjugate acids and bases. So in other words, on the reactant side, we've got our HCl, which behaves as an acid, but yet the Cl minus on the right-hand side behaves as a base. It's a base because in the reverse reaction of that, it will accept a proton and become HCl again. I mean, that's just the point there on that. H2O, on the other hand, is a base in the reactant side on the left-hand side, but yet the hydronium ion then it behaves like an acid because it becomes a proton donor. Then in the reverse reaction, it donates a proton to the to the Cl, making HCl, and renders H2O. Okay, so yet again, really importantly, strong acids ionize fully. HCl in water, which means in an aqueous solution, will form Cl minus and H plus in aqueous solution. Strong bases ionize fully. Sodium hydroxide will form Na plus and OH minus in solution. They ionize fully. That's the point, and this has got to do with the molarity thing that I said. 1 molar HCl produces 1 molar H plus because it ionizes fully. It's really, really important. Strong bases the same. Weak acids ionize partially. By the definition of a weak acid, that this is what happens. They ionize only partially and donate protons only partially. That's the point. Weak bases the same. Not to overcook this point, but a strong acid produces a weak conjugate base. So HCl would be a strong acid, but Cl minus would be then a weak base. That's the point there for that. A weak conjugate base, that is. And then similarly, a strong base produces a weak conjugate acid. And that's the only point there. Okay, so we can write what are called equilibrium constants, but in these cases for acids and bases they're actually called ionization constants, but the two are interchangeable. So for reversible reactions involving weak acids and weak bases, two differences: we don't use the H2O because it has a concentration, if you like, of 1. It's 100% because the stuff is dissolved in H2O, so the H2O is omitted. It has a value of 1. Instead of using Kc, we use Ka for acid ionization constant and Kb for base ionization constant. And Ka and Kb are describe the extent of ionization, and so when you get them in tables, Ka and Kb values, it tells the extent of ionization. That's the point there. Okay, so just like the equilibrium constants, it's the very same thing. Reactants are on the left side. They go on the lower of the line, and formation, our products, go on the upper line in terms of concentrations of the square brackets. That's all you do. Omit the H2O out of it, and you end up then just with a single reactant, and you've got 2 products on the other side. Knowing concentrations then, for example, this balanced equation here, this reversible reaction, we end up getting a Ka of 1.8 by 10 to the minus 5. The stronger the acid, the greater the tendency to transfer a proton to H2O, and also the higher the Ka value. And again, we see this in the table later on. We see values for an acid, it runs from the weakest, which is approximately in the 10 to the minus 19 region, to above 10 to the minus 5, into the positive, the 55 value, and beyond that to very strong for sulfuric, nitric, and hydrochloric acid. Okay, but at the lower end of the scale is 10 to the minus 19, so this is quite a high value. 10 to the minus 5 is of the order of 15 zeros, if you understand the notations here for indices. So this time for base ionization constant Kb, we've got another reversible reaction. We've got our reactants on the lower line, got the products on the upper line. Strike off the H2O as per usual, have your concentrations with the square brackets, and then take a example of a reversible reaction. In this case we have ammonia with H2O, and our Kb then, our constant for ionization for a base, is written like this, and we get a value of 1.8 again by 10 to the minus 5. And this too then is, quite a high concentration. Strength. The stronger the base, the greater the tendency to accept a proton from H2O, and therefore the higher the Kb value. So again, 10 to the minus 5 is well up there if you're talking in respect to 10 to the minus 10 and 10 to the minus 15s for weaker bases. This is relatively strong. Okay, look, this is great. So here's a table then where we have our acids, here's where we have our bases, here's our Ka, our ionization constant for the acid. We range from large all the way down to, I was saying, the 10 to the minus 19, very low strength. So you've got that, and you can see from the table what it is. We did have a 10 to the minus 5 just a moment ago, and this is the one we're talking about. On the other side we've got our bases, and again we've got our very small, and that runs from then 10 to the minus 16 and keep going. We get a 55.5 for good old OH minus, and for sulfide ion we've got a value of 1 by 10 to the 5. Let me just drag that over so you can see that just a bit better. And that's the point I'm trying to make there again with this. Okay, so these are the values running from very small right up to 1 by 10 to the minus, or 10 to the plus 5 this time. These are 10 to the minus 6, or very, very small strength. Okay, now remember, water with its hydrogen bonding, very, very strong hydrogen bonding, its polar bonding, has the ability to pull hydrogen ions off other water molecules if you get a right collision at a right momentum, right energy, etc., etc. And if that happens, then you end up going from H2O to H3O plus, okay? And conversely, you end up with an OH minus, for a hydrogen that's been lost from another water molecule. Okay, and that being the case then, this means that we can also quote a Kw, an ionization constant for water as well. Okay, again, we only have a single line, no lower line, because it's only water in the reactants, and that has a value of 1, so therefore you have nothing on the lower line. Okay. It's temperature dependent at 25 degrees Celsius. Equilibrium concentrations in pure water are equal to concentration of hydronium equals concentration of hydroxide equals 1 by 10 to the minus 7 molar. Okay, so that's the figure you've got for that. By experimentation, this is produced. Kw, therefore, is you multiply, it's the product of the two of these concentrations. There you go, 1 by 1 gives a simple 1, 10 to the minus 7 by 10 to the minus 7, you add the indices, that's the rule. That's the rule for indices. When you multiply them, add them, and you get 10 to the minus 14. So there's your Kw ionization constant for water. And 10 to the minus 14, remember, relatively low number. Interesting Kw problem here that we have. We've got hydrochloric acid in water. Okay, so solution gives hydronium ions, and we get our Cl minus ions as well. We've got to calculate the OH minus concentration. We've got a lot of H's going into this solution, okay? So that means that we're going to lose some of the OH minuses that would be present, the hydroxides. They're going to combine with hydrogens from the dissociation of the HCl, and they're going to make more water. That's the idea there. So this figure is going to be quite low. It was 1 by 10 to the minus 7 just a moment ago, but we're going to see that it goes down quite a bit. I'm just zooming down to the end there. You can see that it's gone from 10 to the minus 7 to 10 to the minus 11. That's a 1,000. It's a 4-0 change. So that's what, 10,000 in the difference. So that's the kind of thing we're talking. But in any case, we have to calculate the concentration of the OH minus of a 0.00015 molar HCl. Now this is strong acid, and remember what I said, strong acid means that we're going to get full dissociation. So our hydrogen concentration is going to be equal to this figure as well. Okay, so there we have it. Hydronium ion concentration is this molarity, same as what we had at the start. We've got the Kw for water. Okay, the ionization constant is 1 by 10 to the minus 14. We are looking for the OH minus. We now have the H3O by dissociation with the acid added. It's going to be the same figure as this figure here. It's changed slightly, the notation's different. It's the exact same thing though. 1.5 by 10 to the minus 4 is the exact same as 0.00015. Okay, that's the point there. We've got a simple calculation. We've got to switch this figure from the side it's on to the other side. It is multiplied because of the brackets. You switch it, it'll divide. Next line, you can see it is divided right there. And we get a figure for OH minus of 6.7 by 10 to the minus 11. Much reduced. It was by 10 to the minus 7. Now it's 10 to the minus 11. That is a fourfold in the zeros, I believe. That is a 10,000 order of change.